In this class, we will continue our discussion of a one-way analysis of variance by completing the summary table for our example. We will start with the summary table as we have discussed it to this point. Now, let's see if we can complete a summary table using the example we cited earlier. To remind you, we assume that the mean Beck depression inventory for the experimental group equaled 10, the mean BDI for the standard treatment group equaled 14, and the mean of the no treatment group equaled 21. We also assumed we had a sample of 30 participants, 10 participants in each group. But before going to the next slide, see if you can determine the degree of freedom for each component of the summary table. Using the formula from the slide in the previous class, we find sums of squares treatment is equal to 620. We multiply 10, or the size for each group, times the sum of the deviations squared for each mean minus the grand mean. We sum all those up and we get 620. Because sums of squares treatment plus sums of squares error equals sums of squares total in one-way ANOVA, that means that 620 plus sums of squares error will equal 2,500, or sums of squares total. That means that sums of squares error is equal to 2,500 minus 620, or 1880. In this slide, we have the summary table updated with sums of squares added. Before going to the next slide, see if you can compute the following: mean squares for both treatment and error, and the F ratio. In this answer, the mean squares treatment, or treatment variance, is sums of squares treatment divided by degrees of freedom treatment. 620 divided by 2 equals 310. The sums of squares error, or the error variance, is sums of squares error divided by degrees of freedom error, or 1880 divided by 27 equal to 69.63. The F ratio is the mean square treatment divided by mean square error, treatment over error, or 310 divided by 66.63 equal to 4.54. The probability associated with F equal to 4.54 is 0.021. Before going to the next slide, see if you can answer the following question. What is the critical value we would use to test the null hypothesis? And should we accept or reject the null hypothesis? We can learn the critical value by using the F table. When alpha is equal to 0.05 and degrees of freedom in the numerator, or treatment, equals 2, and degrees of freedom denominator, or error, equals 27, the critical value is 3.35. Because the test statistic F equals 4.54, This exceeds the critical value f equal to 3.35. As a result, we would reject the null hypothesis and conclude that the means do not equal each other, or that the means do not come from the same population. Referring to the significance column, we find that the probability associated with f equal to 4.54 is 0.021. When alpha is equal to 0.05, p is equal to 0.05 at the critical value. When a test statistic exceeds the critical value, the probability associated with that test statistic is less than 0.05. An interesting point that now occurs is that although the results of this experiment tell us that the null hypothesis is true, it does not tell us what part of the statement is not true. For example, it is possible that mean 1 is less than mean 3, but may not be significantly different from mean 2. It could also mean that mean 2 is less than mean 3. As a result, significant ANOVA results with more than 2 means will have to be evaluated further with follow-up tests to learn where differences lie between the means of the levels of the independent variable. It's to that topic we turn next.